This animation shows the experimental design and results of Einstein's photoelectric effect experiment, which tested Planck's hypothesis at the time that light energy was quantized. That means light, in addition to having a wave nature, also had a particle nature, which was a completely contradictory and outlandish idea at the time. Though Planck's idea did enable him to explain the black-body radiation curves. Alright, for this experimental design, Einstein had to think of a way of testing Planck's notion that the energy of a photon, a quantum of light, was associated with its wave nature, such that the higher the frequency of the light, the greater the energy per packet of light, per individual photon. Also, the energy per photon was inversely proportional to the wavelength. So, Einstein set up a piece of metal, a metal plate, upon which he shined laser light of a particular color, one wavelength at a time, and of a particular intensity. It was already known that metals have relatively low attraction for their valence electrons, so the thinking was if sufficient energy light was shined upon the metal, electrons would be ejected. And the brighter, or the higher the intensity of the laser light shined upon the metal, the greater the kinetic energy of the ejected electrons, because by conservation of energy, the electrons ejected would have absorbed more energy. So Einstein started with the longer wavelengths of light, like the red. So as you see here, just into the red region, 670, 680, and there was no electron ejection, so going by the classical wave theory of light, just increase the intensity, the brightness, brighter, 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 the electron should be ejected, and with pretty high kinetic energy, yet that was not observed at all. So bringing the intensity or brightness back down, I'll make it about 25% roughly. Einstein used shorter wavelength light or laser light into the yellow region, and again there's orange, yellow. No electrons were ejected, so again increasing the total energy hitting the plate per second, putting more and more yellow lasers or higher energy, higher power lasers, zero electron ejection. So this started to cast some doubt onto the wave nature of light, because it's such a high intensity, it's very high amplitude waves hitting the metal, and no electrons were being ejected, even though there's a significant increase in energy that's being shined upon the metal plate. On the other hand, this was starting to at least begin to go along with Planck's theory. So far, the wavelengths used were very, relatively longer, so perhaps any photons hitting the surface just did not have enough energy per photon because the wavelengths were so long or large. These photons, when they hit electrons in the metal atoms, just didn't have enough energy to knock them out. So on went the experiment, bringing the intensity back down, and over to the green. There it is. At this point, according to Planck's hypothesis, with a short enough wavelength, the energy per photon was great enough, large enough to, upon contact with an electron in a metal atom, when that photon of sufficient energy was absorbed by the electron, it was enough to knock the electron or cause the electron to overcome its attraction to the nucleus and knock it out of the atom. These ejected electrons were measured as a current at the other plate, which was positively charged. So the electrons were directed in this vacuum tube. There couldn't be any interfering air or any other particles in that vacuum tube. So this entire experimental design really took some thought and careful construction, but in the end, I guess the Nobel Committee thought this was genius, which it was. Einstein won his only Nobel Prize for this experiment that could easily have refuted Planck's idea, but ended up being the first of many experiments to support it. Two things to note. The kinetic energy of the ejected electrons, or the maximum kinetic energy, was the same for each of the ejected electrons. This was measured in another way, which I'm not going to show right now. But you could see from the animation that the electrons ejected are all traveling at the same speed, they have the same kinetic energy, and that again suggests that the photons that hit the electrons each had the same energy from this uniform wavelength, which again is consistent with Planck's equation. The second point is, with the greater intensity, if you look at the particle nature of light, that would imply there's no amplitude to a particle. It just means that there would be more photons hitting the metal surface per second. So the rate of photon collision with the surface is greater with brighter light, greater intensity. So that is what Einstein then did. So crank up the intensity. Much brighter green light. And the number of electrons ejected per second increased dramatically, as was measured by a great increase in current at the other plate. So this again is consistent with the particle nature of light. Increased intensity, more particles hitting the surface per second. There was no increase in kinetic energy of the ejected electrons, even though there's a lot more energy hitting the surface per second. Completely consistent with Planck's equation, E equals hf or hc over lambda. Lambda didn't change, frequency didn't change, energy per photon didn't change. Therefore, the kinetic energy of the ejected electrons should not change. However, at the greater intensity, there should be a lot more electrons ejected per second, because there are a lot more photons hitting the surface per second. Don't make the mistake of saying a lot more photons. It's got to be a rate. More photons hitting per second, more electrons ejected per second, same kinetic energy. So now bringing the intensity back down, should have fewer electrons ejected per second, but no change in the kinetic energy of the electrons ejected, and that's what you see. But now predictions could begin to be made with even shorter wavelength light, the blue, the violet. These are higher energy photons by Planck's equation. And with the same intensity, there should be the same number of photons hitting the surface per second and the same number of electrons ejected per second, but they should have a lot more kinetic energy because they're being hit by much higher energy photons. Not higher kinetic energy photons, there's no such thing. All photons move at the same speed and they have no mass. So going to lower wavelengths from 532 to into the 400s, you see the electrons ejected, same number ejected per second as before with the lower intensity, but now they're coming out with a lot more kinetic energy because they were hit by higher energy photons. Increase the intensity and same kinetic energy photons, electrons ejected, but a lot more of them ejected per second because the higher intensity there are greater number of photons hitting the electrons per second. Again, bringing the intensity down. Nothing happens to the kinetic energy of the ejected electrons, given that using the same wavelength, same frequency light, same energy per photon. So bringing it all the way down to the even shorter wavelength, the end of the visible spectrum, violet, and the electrons ejected are even faster than they were with the blue or the green. And there were no electrons ejected for the yellow or the red. No photon had sufficient energy to, after absorption by an electron, knock the electron away from the nucleus of a given metal atom there. So this experiment, of course, was repeated thousands, perhaps hundreds of thousands of times, with different metals, different wavelengths of light, even into the invisible region, ultraviolet, infrared, etc., etc. And the same consistent results, supporting results for Planck's hypothesis that light does have a particle photon nature, and it could be quantified based on its wave nature using the variables frequency and wavelength. So here I'll crank up the intensity of the violet laser. Same kinetic energy of ejected electrons, but a lot more of them ejected per second. And then one last thing, as a way to measure the kinetic energy of the ejected electrons, a battery was hooked up to the metal plates and reversed the potential of the plates, or the charge of the plates, such as to stop the electrons from going towards the plate on the right by making that plate negative. So as you can see, as I change the potential difference and make it more and more negative, there's something called the stopping potential or stopping potential difference, and using simple physics equations such as the work on these electrons, the work required to change their kinetic energy would just be the charge of the electrons times the change in potential difference. There was a direct way to measure the kinetic energy of the ejected electrons. So the main equations and main calculations that we get from the photoelectric effect type of setup or experiment is that the energy of the photons used, based on the wavelength or frequency laser that was used, the difference between that and the minimum energy required to knock out the most loosely bound electron from a metal atom at the surface. So I'll draw that in a picture. Here's a metal atom. Here's an electron in the metal atom. Here comes a photon of a particular energy. So I'll make up fake numbers here. Let's say this has 10 energy units. I won't use joules or EVs, just 10 energy units. And the minimum energy to knock this electron away from the nucleus, let's say, is 6 energy units. So 6 energy units required to knock that electron, to overcome this direct attraction to the nucleus. Well, there's conservation of energy, so how much kinetic energy would the ejected electron have once it's knocked out of the atom? Well, it absorbed the photon, it absorbed 10 energy units. 6 of those units were required to raise its potential energy, its positional energy, to knock it out of the atom. So the ejected electron would have 4 energy units of motion, kinetic energy. So that's the equation. But of course, nobody's going to write minimum energy to knock out the most loosely blah 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 every time. That's far too tedious. So this equation becomes energy per photon minus the very convenient, well, the symbol isn't that convenient, the work function is what they call it. Fancy name for the minimum energy required to knock the most loosely bound electron from a metal atom at the surface. So these are not gas phase atoms or anything like that. These are the solid metal. So it's the work function of the particular metal. That's what all those words mean. And the difference between those two things will be the kinetic energy of the ejected electron. So when the energy of the photon just equals the work function of the metal, there will be zero kinetic energy of the ejected electron. It just barely is making it out of the atom. So in the photoelectric effect experiment, the experimenter will look for the minimum frequency of light, the minimum energy per photon required to just barely start ejecting the electrons. So this is a key equation, and the variables that make it up can be further elucidated. This could be HF. The work function is going to be, we can equate that with the energy of a photon that just barely ejects an electron, not quite. So this would be, we could call this HF min. Whatever that minimum frequency light times H will give you the photon that almost knocks the electron out of the atom. So that's going to equal the work function, and that's going to equal kinetic energy of ejected electron will be the mass of an electron times the speed of the electron squared divided by 2. So that's another more detailed formula. Okay, so we'll do more specific problems involving these variables later.